5-2 Notes for Calculus 1. Previous section, you learned all about wonderful Riemann sums. And the goal of the Riemann sums was to approximate the area under the curve. We had the left, right, and midpoint Riemann sums that we did, but the key was in the majority of those scenarios that we were looking at, we were dealing with all non-negative functions. So if you recall, we had, let's say we had the axis, and then we had, let's say, a curve like this, and then we would find the area between here and here, right? But everything was above the x-axis. So that is not always the case with curves, right? Sometimes curves go below the x-axis. So what is that actually going to mean in the scope of a problem? So we start with the function f of x equals 1 minus x squared. Suppose we're asked to compute the left Riemann sum on 0, 3 with 6 subintervals, and i.e. rectangles, right? So let's do just a brief run through from our previous section. So what we would do 3 minus 0 over 6 to get 0.5 for our change of x. So we would start at 0 and add 0.5 as we went until we got to 3, and we would end up with these values. And since we're doing a left Riemann sum, we would ignore the 3, and we would have our basically our heights measured at these values of x, or x star k. So if you look at the picture right here, this is a graph of 1 minus x squared. So this is the, look at the curve right here. So this basically is the graph, right? So from that graph, we're basically creating a situation where all the left points of the rectangles create the heights. So if you look at them all here, we get that, and then this one looks like there is no rectangle there. So you basically end up with the same thing, but what is different? So we had all of the ones before were rectangles before or above. Now we actually have 3 below the axis. So what does that mean exactly? Well, if we do the Riemann sum calculation, which we have discussed before, in which we take all of the x star k's and multiply by our change. I need a writing utensil. Change of x, right? Change of x. Then what do we get? Well, our change of x is over here. All our f ofs, which you've seen before, our heights. We're going through and taking all of these values here and subbing them in, right? So you can see that there are these two. Let's mark these. So these two are here and here, right? Then we have our interesting rectangle that creates 0, so there is no rectangle. But then look what happens on the last 3, these guys. We actually have a negative contribution to the area. Negative contribution. So if the rectangle to the x-axis is below the axis, then it's a negative area. So what do we end up with in the end here? We end up with an area of negative 3.875. This is actually referred to as the net area. And basically what that means is that you're taking the area, the positive area, and the negative area, and you're adding them together, and whatever you get, you get. If you get more area in terms of it being negative, that means there's more area to the x-axis below the curve than area above. So more below than above. So that's how net area works in the scope of what we're doing, and it becomes a very important part of the remaining problems that we're going to be doing over the next few sections, is we'll be finding lots of net area. But in the previous section, we really concentrated on driving home approximate area, but now the key is that we want to find that exact area. So no more using rectangles. We need to know exactly what that area is. And how did we do it? Well, I gave you a preview. If you recall, I gave you this, where I said, hey, if you look at these are each rectangle. These are summing up the rectangles. And then this limit is saying take as many rectangles as humanly possible to sum up after you take their product. That is actually equivalent to what we call is a definite integral. And that is right here. Okay, right there. So if you look at this definite integral, it looks almost exactly the same, except it has what are called limits of integration. So this basically represents your two endpoints of your area. So again, if we have a curve like this, and we want to find the area from here to here, then A and B would be those values that you see on the integral right here. So you're not, from now on, you're, other than doing problems on, just testing that you know it, you're not really going to see this anymore. This was a one section deal, 5-1. Now you're going to be seeing this terminology because we really would rather see the exact area than nothing else. And by the way, that exact area is going to be the net area of what you're trying to find, whatever that area is under the curve. Okay, so just so you can see here, they just said just as a summary, exact area is the definite integral under the curve. So just when you're looking at this, when you're looking at the formula right here, so let me erase all this stuff. So when you're looking at this specific formula and you're breaking it down, remember your f of x is the same. It's actually representing the heights of the rectangles, just like it did in the in the formula for Riemann sums. So that means if we're trying to represent the sum of the heights, that is going to be basically this and this. This is why you cannot forget the dx, because essentially it's replacing the sum of x in the Riemann sum formula, which means it has to be there. No matter whether you forget it or not, it must be there, so don't forget. So as I wrote here, you cannot forget the dx when you're writing your integrals. Don't. Okay, so what we're going to do next is, in the next section, we're going to get into, in section 5.3, we're going to get into actually using calculus methods for determining a definite integral. But before we do that, it is very important to mention some properties and talk about how area is manipulated within an integral. It's very important to go there before we get into those methods so there's full understanding. So for example, for number 1 here, we're asked to graph the integrand 2x minus 6. Instead of using calculus, we're just going to use what they call familiar area formulas. This is a valuable step. You do not do this all but maybe once or twice, but it's valuable for you to see exactly what you're trying to do in these problems. Okay, so the first thing we want to do here is we want to talk about this. So what exactly in words is this saying? This is saying that you want to find the area under the curve 2x minus 6 from x equals 1 to 6. That's exactly what this is saying. So even though this is the definite integral, a definite integral 1 to 6, 2x minus 6, the actual reality of the situation is you're just trying to graph the line 2x minus 6, and you're trying to find the area to the curve between 1 and 6 on the graph. So the first thing we're going to do here is we're going to make a quick sketch of 2x minus 6. So no calculus, just using a little geometry. So what are the things that are important? So if you set 2x minus 6 equal to 0, for example, and solve, you're going to get that x is equal to 3 when y is 0, right? So that means we're going through the point 3, 0. Let me get some numbers on here. So we have a scale, right? And 2, 4, 6, -2, -4, -6. So we have a nice scale. So now we have the point 3, 0. Actually, let's use a different color. So that's the point 3, 0 right there. We know that this is going to go through some other points. We want to, let's say, where are we going from? We're going from 1 to 6. So we're about going from here to here. So it would be wise probably to sub these in. So if you put 1 in here, forget about, we're not looking at the integral. We're just looking at the expression 2x minus 6. If we plug 1 in, we get -4, which means there's a point here at 1, -4. And if we plug 6 in, we get 6. So there's a point here at 6, 6. So we can draw this line now. And we now have a graph of the function 2x minus 6. So that's the first step of this. Now what we're trying to find is the area under the curve. So what does that look like? Well, what we need to do is we need to drop lines to the x-axis, right? And then we need to shade in that area. So basically, this is the area under the curve after 3. And this is the area under, even though it's under the curve, it's sort of over, but it's the area under the curve from 1 to 3. So what we're trying to do is we're trying to find the area of these right triangles, and that will actually, believe it or not, give us the answer to this. So what does that entail for this? Well, area is equal to half base times height in a triangle. So that means we can pretty easily find these values. So for example, here, so this is 2. We know that this is, it looks like 4. Okay. We know that this is 6. And we know that this is 3. Okay. So what does that look like? So the area of the big triangle is equal to 1/2 base 3 height 6. So what do we get? We get 9 if we multiply that out. What about the area of the smaller triangle? That's going to be 1/2 2 times 4, which is going to give you 4. So by looking at this picture, we basically have these two areas. Now, does that mean that the area under the curve is 13 for our problem? Hopefully after, going through all this, you say no, because any area below the curve is negative. So what the integral of 6 to 1 of 2x minus 6 dx is going to be the equivalent of taking 9 plus the negative version of the area on the bottom, which is going to give us 5. So this integral, which we are going to be calculating using calculus in the next section, actually gives us a true area of 5. Now note, remember, this is the net area because it's a definite integral, right? Net area. And it's taking into account positive and negative area. So you'll never really use triangles again to do this unless you do it in the homework on labs or something. This is all going to be done with calculus, but this is a very valuable way for a student to see that all this is just glorified area computations. The thing is, it was really easy to do because it was a straight line function. If I had given you the same function, but it was a curve, what shape are we going to use? We're not. We can't use some crazy, we don't have a lot of circular shapes that we can use that will bump up against something. Doesn't work that way. So we can do this for now because we have a line, but that is going to be the area for that particular integral, and that's what that means. Okay, so let's just cover some basic properties of integrals. Not a lot that you have to memorize per se, you just have to be aware of these when the time comes. So for example, the first one you should be very familiar with. We've really covered it already, where we say if we have the integral of a to b of f of x plus or minus gx, then we're allowed to separate it into two different integrals. So we already used that when we use polynomials and functions that are split by plus and minus signs. It was the same rule for limits and derivatives. It just comes over. Now, let's talk to ones that are more important. So this one is super important. It says the area from A to A, so from A to A of the function is under the function is always equal to 0. Okay, so I'm going to draw a graph. So let's say you did one of our graphs again where it looks like this, right? So you have something that looks like that. And let's say an interval a to b, and you want to find the area from A to A. Okay, so you have to realize that we're finding area. And when you go from A to A, what is this right here? This is a straight line. So there is no area above a straight line at all, or on a straight line. So area is made up by dimensions. So therefore, the area at any one value under a curve is going to be 0. So if I picked a random value over here called C, and I said how much area is above C, it's 0. There is none. But if I said C to B, then I can start accumulating this area using methods that we're going to be using from here on out. So this actually does come into play sometimes, so be aware of it. Next, if you have the area from b to a of f of x dx, let's say you find that actually the best way to put this is, if you have an integral, you always want the lower number, the smaller number, to be on the bottom. So let's say you were given the bigger number on the bottom of a function. So let's say 2x plus 1, right? So this is actually going to be equal to the equivalent of, if you switch the limits so that they actually go in the proper order, then you would take the negation of the same function before you integrate. So this also comes up sometimes where you should immediately have a big warning symbol in your brain that comes up that says, wait, we should not be having a larger number on the bottom part of the integral, which means I must flip it and put a negative multiple on the end of it. Okay, so the last one, another graph, just to make sure we can visualize it. So let's say you have a curve here. We're going to do the same setup. Let's say you have A here, C here, and you're looking to find that area. So that would be this, right? You want to find the area from A to C. Well, what this is saying is that if you pick a point B in the middle and you go like that, so this entire area will be equivalent to the area here plus the area here. Okay, it's really logical, right? But this basically shows that to you because this is the area from A to B, this is the area from B to C. If you add that, you get the area from A to C. So a lot of very straightforward formulas, but some of them, like these, are not extremely apparent right in the beginning, but you need to be able to work that out when you go through some of the problems. Okay, so this is the last page. I'm just going to go through a couple scenarios that help you understand this area stuff as best as possible. These are very minor type problems that are just used to further your understanding of the material. It says, let's look at the following diagram. So let's say we have the function y equals f of x, which is this curve that looks like it goes from A to D. Okay, A to D. So here to here. Along the way, we also have some other points, B and C, and we're asked to answer the following based on the diagram. All right? So let's say I was asking for the area under the curve from A to A of f of x dx. Well, again, anytime you go from A to itself under a curve, or any number to itself, you always have an area of 0. What about if you want to go from A to B? So A to B. So that's going to be essentially the area under the curve. So the curve from A to B is here, right? This is your curve. So what's the area under the curve? It looks like 12. So that means that's it. It's 12. Now, what if you go from A to C in this problem? Okay, so we already know A to B is 12. But what do we have to do with the 15? So note, when I write area on a picture, I'm going to write whatever the positive number value is that represents that area. But in terms of integration, we know area that's below the x-axis is negative, which means the area from A to C, the best way to put it is net area, remember? So any indefinite integral, or definite integral, not indefinite, any definite integral is net area. So we are going to get -3 now, accumulated area. So last one, what about A to D? Well, again, we're going to be 12 plus -15, but then we're going to add on another +8 for above the axis. So we're going to get a 5 resulting area for everything. So very straightforward, very simple for most students to understand. But again, I want to point out that when they write the area, it's always there's no such thing as you can't write negative area. But conceptually, it is a negative impact or contribution to the net area. So we have to include that when we're doing it. All right, so let's take a look at how these properties actually come together. All right. So what I gave you up top was a bunch of given information. So what do you know? You know that from 0 to 5 of the function f of x, there's a net area of 3. Of the same function, if you go from 0 to 7, there's a net area of -10. All right. Now we move to a different function, g of x. Let's say we go from 0 to 5. Under the area g of x, there's a net area of 14. And for the same g of x, if you go from 5 to 9, there's an area of -8. So these are actually provided to you in an effort to finish and complete A through E in number 2. So look at A. It says, what is the area from 0 to 7 of 2 times the function? Well, if you look already, we've already been given the area of 0 to 7 of just the function, but you've learned that when you take an integral, you know that a constant is just coming along for the ride. So the constant can move outside the integral, and we end up with this by itself, which we already know is equal to -10, which means we know that the resulting net area is going to be -20. Okay, it's just a simple application of the basic rules for definite integrals. That's all it is. So that's going to be -20. So what about B? Okay, so let's say we have 0 to 5 of f of x plus 3g of x dx. So this plus sign. So what are we doing? We're going back to we're going back to this, right? So if we have a plus sign, we can split that into 2 different integrals. So f of x dx plus 3 times 0 to 5 of g of x dx. So note, do you see how the limits of integration actually are the same on both of them? That is something that you didn't have to do before. Now you got to make sure that you do that. So again, if you look up here, we've already been given this value. So this value here is 3. Over here, we've also been given this value which is here, and it's 14. Which means if 3 plus 3 times 14, we do that math, we're going to get an area of 45 as our result. All right, so let's move on to a little bit more with our values here. So what if we did the definite integral of 5 to 0 f of x dx? So as I stated before, a light bulb should be going off in your head and saying, this is not right. It's like the lower number should always be smaller than the bigger number. And if it's not, that means we have to immediately return to this property right here and make sure that it is that way. But the only way to do that is to put a negative multiple on it, flip, and get this. But again, Don't we already know what 0 to 5 of f of x dx is going to be? It is. So we're going to get negative and then 3. So that means our result, so this whole thing here is 3. And then a negative on it gets you negative 3. So this is going to be our net area for the problem. Okay, so this is where it gets a little bit more involved. So let's take a peek at the following. D. It says, what is the area under the curve G from 0 to 9? Okay, so we're basically only concentrating on G, but if you look up here, we don't have the area from 0 to 9. But, interestingly enough, this tells you the area from 0 to 5, and this tells you the area from 5 to 9. So according to this rule, we should be able to just add those together to get the full area. So let's write that out. So this is equal to the area from 0 to 5 of g of x dx plus the area of 5 to 9 of g of x dx, which is going to give us the two areas that are provided up here. 14 plus negative 8, which is going to give you 6. That is your net area. Now, I want to do a little bit of a side note here, an aside, in the fact that some students get really messed up by this in their heads because they look at this and they're not quite understanding. Because they'll say, well, aren't you including 5 twice? Okay, I've heard that many times over the years, and the answer is absolutely not. Because what did we learn about the area at any one value? So at the variable a here, right, there's no area. So at the number 5, there's no area, so we're not repeating anything. So sometimes a difficult concept to really comprehend, but this is perfectly fine in terms of something you can do. Okay, so last problem here. So 5 to 7 of f of x dx. Okay, so we're concentrating just on the f of x value. So if you look up there, we don't have 5 to 7 anywhere. But interestingly enough, we do have 0 to 5 and 0 to 7. So what could we do with those quantities that would allow us to actually get just 5 to 7? Hopefully right away you see that subtraction is going to be the key concept of the day. So for this one, so we're going to do 0 to 7 of f of x dx, which is going to give us all the area from 0 to 7. And if we subtract all the area from 0 to 5, then that should give us all the area from 5 to 7, according to our rules we just looked at. So this area, according to this, is negative 10, and the other area is 3. So therefore, if you do the math, you get negative 13 as the net area for our problem. And again, all of these are net areas, and that is basically what we're going to be concentrating on as we move to the next section and we get into really serious integration. Right now, you just know the basics.